So we're going to look at that remainder term, and this remainder term kind of shows up in the Lagrange form of the error, and also in the integral form of the error. And basically, it's going to be using a mean value theorem type of thinking to be able to justify this. Okay, so if you recall, the truncated remainder for the Taylor polynomial was, our R of n was just going to be this is going to be the rest of the terms from, n plus 1. So this is going to be f of n plus 1 of c n plus 1 factorial. Okay, and it's going to be, x minus c to the n plus 1. Okay, so it's going to be the sum of rest of those terms from n equals n to infinity. Okay, so this is the truncated form. But we can just say that the remaining set of remainder of that series, okay, the rest of the series that we chop it off from, we can calculate the error, which this is again represents the error. We can calculate the error using a form of the next term, okay, and we're going to justify this using, first of all, using just the first term. So here we're going to use just a Maclaurin series. So it's going to be centered at 0. Okay, so it's going to be centered at 0 here. And this point B is going to be some point between the center and the point that we're trying to estimate. Okay, and you can see that this kind of falls within the mean value theorem. We know that there is a derivative somewhere in between here and here, which will, if we can use as the secant line, which then we can use as a linear approximation from the red point to the blue point. Okay, that's essentially, we can use a mean value theorem in that way. So if we look at the Maclaurin series, and we just look at the first two terms of the Maclaurin series, so the first term essentially. Okay, so we have our p of x, and then this r and the remainder term, okay, is going to be this, right? We have our p of x, the p of x represents our whatever polynomial that we cut it off at, and then we have a remainder. So looking at this, the first term then, the very first term of that function, okay, this is the actual value of the function will be the first term plus the remainder, okay? And if you recall this, if we have the first term and we use the slope of the slope, which is the derivative, which is related to the second term of that polynomial, okay, if we use a slope, we can then use a linear approximation. So that purple line here, this purple line essentially means, I'm just going to highlight it, this line and this line are they're essentially the same thing. And well, really these two things are the same thing. So what we can then say is that, well, by using the b value, we can invoke the mean value theorem. We know that there is this point somewhere in there that's going to give us the exact slope. Okay, so we're not going to, estimate, have some tangent slope like that. We're going to say we can get to the exact value of the solution by knowing that there is some point in between the center and the point we're estimating. Because it's smooth and continuous, we know that there is this point somewhere in there that will give us a tangent slope, and we'll use that tangent slope to calculate the exact value of the function. Okay, and that exact value represents the, this part of that exact value represents the error term. So basically the remainder of r of 0 is going to be, the remainder for the 0th term is going to be the f prime b of x, right, which is essentially our a1 term. Okay, so our a1 term, or the next term, so n plus 1, so 0 plus 1, is going to give us the error term. Okay, and we know that we can get exactly the error. Okay, we may not be able to find it, but we know that it exists. There's some point b that will allow us to get the exact error. Okay, so that's, just as one term. So that's our linear approximation. Well, if we increase the number of terms, make it into a quadratic. So we just add one more term to this. So our remainder is R1. It's going to be based on these first two terms. This is then, this becomes essentially our quadratic. If we kind of think of what that next term is going to be, this is going to be our quadratic estimation. Okay, and this idea then is that, well, there is a line that approximates that curve, but there's also a quadratic, okay, that is going to be the perfect quadratic that will fit that. That's not a great looking quadratic, but there is actually a perfect quadratic, and we don't know exactly where that quadratic is, but we know that we can find the value of that quadratic at point B. And that point B we just know exists by extension of the mean value theorem to the quadratic sense. So this is our linear mean value theorem. There is, in essence, the equivalent quadratic mean value theorem saying that there is this perfect sloped quadratic which will get us from that point to that point. And that quadratic is going to be based on this quadratic term, which is our R1 term. So we can then say that the remainder term for, when we have the remainder first of n equals 1 is going to be based on this term here, which is A2. Okay, so it's going to be this value of n plus 2. And again, we're not going to use the center at C. We're going to find the slope at some point B, and which gives us the perfect quadratic that will estimate that point. Right now, if we use C, the quadratic that we're going to use is going to be, some other quadratic that doesn't quite match that curve. Okay, and maybe it's, it's going to look something like that, right? And it's not going to match the curve very well because it's centered at C. But there is some point B which will calculate the quadratic that will approximate that, will fit that curve perfectly between the center point and our point that we're estimating. And we know that it exists by the mean value theorem. Really, it's an extension of the mean value theorem. So then if that's the case, we're just extending this mean value theorem to this idea that there's this possible B for a quadratic. Well, there's this possible V for a cubic as well once we get to our cubic approximation. And then for our nth approximation, we'll just use the next degree, and we know that that point B exists, and we can use that point B to calculate the exact value of our point that we're trying to estimate. Okay, so then for the cubic, it looks like this. There's a perfect cubic that will estimate, okay, and then so on and so on and so on. And as we get higher and higher terms, these terms actually, remember that these terms are matching much better. So our cubic function might look like this, right? And then we can just find some B that's a very, very small shift of that to match it right on top of, match it right on top of that point. Sorry, I just missed that point. Okay, so this is our justification then. It's essentially we're using this induction to say that we have this mean value theorem for the linear case, we have this mean value theorem for the quadratic case, we have the mean value theorem for the nth degree case. And that's where a remainder term comes from.